Can you hear me? You guys can see the screen, right? All good?
Yeah, can you tell us what's so funny first?
Just I was sharing the syllabus of my elective course. Uh, and we're just laughing at the breadth of topics that's there in that advanced material science course that's going on. Yeah. Anyways, all right. So what we're going to do today is we're going to do a couple of problems with rigid body motion, right? We started looking at pure rotation about a fixed axis last week, and what we'll do is we'll look at a couple of problems regarding those concepts, and then I'll tell you guys the answer to the question, hey Ashish, what's the deal with the exam? So, and then hopefully that'll be like a discussion session whereby you guys ask me questions. If not, if you don't have any questions, then we will likely be ending early. All right. Okay. So what we looked at on last week was that when there's a body, a rigid body in pure rotation, what that means is that it's rotating about a fixed axis, all right, about any axis. The velocity at any point on that rigid body due to that rotation is given by this expression, which is omega crossed with r. Omega here is the angular velocity expressed as a vector about that axis of rotation. So what you've got to do is think of moments and things like that. Your thumb pointing in the direction, in the axis direction, and your fingers curl around in the direction in which your angular velocity is positive. All right. So that gives you the vector direction that you need for the angular velocity. And then for this position vector, this is the beautiful part about looking at rotation. You can define this position vector to that particular point of interest that you're looking at from any point on the rotation axis. It does not matter because of this beautiful cross product over here. You'll always end up getting the shortest possible perpendicular distance from the axis to that point. All right. So it doesn't matter as long as your starting point is anywhere along the rotation axis. This position vector does not matter how you define it. All right. And similarly, we got an expression for the acceleration, which is the same thing, which is your angular acceleration crossed with r. Again, now angular acceleration, you define it the same way as you define your angular velocity, right? Your thumb on your right hand pointing in the axis of rotation, and then your fingers curling in the positive direction for positive angular acceleration. All right. Okay, that crossed with r. Again, r is the same thing. You can find this from any point on the rotation axis to your point of interest. It's great. And then you have this other term, which is radial acceleration. So this first is the tangential acceleration, which is omega crossed with your velocity due to the rotation. So that's just omega crossed with r. Many people, physicists and mathematics people will tell you that this is a triple product, and you can say, all right, cool story. But the way that you find out a triple product is you go from right to left, right? That's just the mathematical way of doing it. So you find out what your rightmost cross product is first, and then you take the cross product of that with whatever is on the left hand side. All right. Okay, so now let's get into it. So we are looking at this problem over here. Right, so what we have is, and this is problem 2 from your problem statement. Let's mark that out. So we have is there's a circular plate which has a radius of 120 millimeters, right? And it's supported by two bearings at A and B. All right. The plate rotates about this rod. So basically these bearings are letting this plate rotate about this rod AB over here, right? So this is your, I'm going to try to draw it and it's going to be terrible, but bear with me. Oh, see, it's so terrible already. But that is your, is that any better? Anyways, whatever. That is your axis of rotation. So this axis over here is your axis of rotation. So along in the AB direction. All right. And you're told that it's moving with a constant angular velocity of 26 radians per second. All right, you're asked that. Knowing that at the instant considered, the velocity of point C is directed towards the right, right? So it's saying that this point is moving this way. So basically what this means is that you're moving, if your thumb is pointing in the direction from A to B, your fingers are curling that way. So this is the axis of rotation, basically. Do you guys understand that? Okay. All right. Well, it's a little detail. It doesn't really matter because no matter which direction it's moving in, you're going to be okay. All right. So you're asked to find the velocity and acceleration of point E. All right. Really easy. We can straight away go out and say that the velocity of point E is going to equal, and this is in pure rotation, right? So this is going to equal whatever your angular velocity is crossed with the position vector of point E. Now, right, we have choices. We can find out the position from all the stuff that is given to us. We can find out the position of point A, and we can find out the position of point B. And both of these points are on the axis of rotation, right? So here you can find out E relative to A, or you can find out E relative to B. And this will give you the exact same answer. And you know what? Just for the sake of saying here, Sheesh, we don't believe you, we'll do it both ways and see if we get the same answer or not. All right? Okay. And then, so this will give you the velocity at point E because, as you see, this is known because we know 26 radians per second, and we'll be able to find out the direction of AB, right? So this is known, and we'll be able to find out what the position vector of E relative to A is, right? Same thing over there. So this will give you your velocity expression. Next, you're also asked to find out what your acceleration is, right? So the acceleration is equal to the angular acceleration crossed with, and for this one, let's just take one because if it works up there, it's going to work down here, right? So we'll just find out E relative to A plus omega crossed with omega crossed with R of E relative to A, like that. All right. Again, here, right, we know this, and we'll be able to find that out, right? Because this thing here, you can just directly plug in. This is just equal to VE, right? We'd seen that in our lecture notes. What about this term over here, right? This obviously, position vector, easy peasy. What about the angular acceleration? What do we know about the angular acceleration?
Zero.
Zero. Why?
Because constant angular velocity.
That's right, constant angular velocity, which means acceleration is zero. So this is zero. So that means that there is no, I keep confusing the two, but there is no tangential acceleration component. All right. Okay, and that's it. That's all we need to do. All right, so let's get into it. So first things first, let's define our angular velocity, right? So angular velocity is going to equal this angular constant over here, right, which is 26 radians per second. So I'm just writing that as omega times the unit vector, I guess. So the axis of rotation, because it's moving to the right, is in the opposite direction of what I was saying, right? So it's going from, it's like that, right? So U of B from B to A. And this is basically just the unit vector in the direction of BA, right? And you guys should know how to find this out. So UBA is just equal to your position vector RBA divided by, well, no, BA is in this direction. So let's just keep it constant, whatever. Keep confusing the issue. It doesn't matter. It's okay. Math is easier for me than drawing stuff out. All right. RBA like that. All right. Does everyone know how to find RBA? From, you have an origin over here. You can find out R of B, right? So RBA is going to equal R of B minus R of A, right? And I'll let you guys figure it out. All right. So this you end up getting minus 100 j hat plus 240 k hat divided by the magnitude, which ends up being 260. All right. Any questions so far, guys? What's the unit of this unit vector?
Isn't it unit?
Millimeters.
No, it's unitless, right? Because millimeters on top, millimeters below, boom, boom, cancels out. So it's unitless. All right, so now we can write out your omega vector as being 26 times the direction of the unit vector. So you have 26 divided times 1 over 260 times minus 100 j hat plus 240 k hat. And what are going to be the units of this guy? Radians per second, right? Because the scalar quantity 26 radians per second, that's what it says. Right? Okay. Next thing, you have to find out what is R of E relative to A, right? So basically this expression over here. R of E relative to A is going to equal RE minus RA, right? And this is in reference to this origin over here. So RE is 120 meters in the X direction. So that's just going to be 120 I hat, right? Minus RA, which is going to be 120 in the Z hat direction, minus 120 so in the Z direction, not Z hat, sorry, Z direction is K hat direction. Mr. Tillotson, your question?
Oh, no, sorry.
All right, so 120 in the K hat direction, and then you go in the J hat direction, Y, up by 80 millimeters, right? So that's plus 80 J hat. And the units of this whole thing is in millimeters, right? And again, we said that for the first part, we'll do it so that we figure it out ourselves, right? So let's just do it. What R of E relative to B is, so that is just RE minus RB. So RE is the same thing, which is 120 I hat minus. Now let's take a look at RB. So RB, you're going 120 in the negative Z direction, so minus 120 K hat. And then you go 180 in the positive Y direction, so 180 J hat, right? So plus 180 J hat. All right, now we just need to find out VE, which is omega crossed with R of E relative to B. We also wanted to find out, let's find out R of E relative to A first, crossed with R of E relative to B. All right, again, can do this by hand. If you guys are gluttons for punishment. But I am not. So let's see. All right, so the first thing, let's define the position vector. So R of E relative to A is equal to, I have 120 in the I hat, I have minus 80 in the J hat, I have minus 120 in the K hat. All right, then you have R of E relative to B, which is 120 in the I hat, minus 180 in the J hat, and plus 120 in the K hat direction. All right, then you want to write out your omega, right? And if you want to be one of the cool kids, you can go out here to the writing assistant and go to over here, go to the Greek lettering and go down and say alpha, beta, gamma is right there. Not gamma, sorry. Crap, what was this? Omega. You can write omega like that. Or what I usually do, and you're going to see me do this a lot, omega looks close enough to a W. We don't use W anywhere else. Don't tell anyone I'm doing this. Just write W like that. All right. So that is basically, we found that that is equal to 0 in the I hat direction, minus 10 in the J hat direction, and 24 in the K hat direction. All right. Awesome. So now we can find out what VE is, right? So for VE, what we're asked to find out is the cross product of omega and R of E relative to A. And we also want to find out the cross product of omega and R of E relative to B. And there you go. You get the exact same answer. All right. So as long as you take the position, the position vector from that point to any point on the axis, you'll always get the same thing. All right. It's just math. So you get that this is equal to. So in Mathematica, what are the units over here for the velocity?
Millimeters a second.
That's right, millimeters per second. So let's just write that as meters per second. So you get this one is 3.12 I hat plus 2.88 J hat plus 1.2 K hat meters per second. And you got the same thing over here. 88 J hat plus 1.2 K hat meters per second, right? So that's your velocity answer, right? Then for the acceleration, this is our expression right here. So the acceleration, and we'll just do it for one of them. You don't need to do it for both. Well, now that you have it set up in Mathematica, let's just confirm it, all right? So acceleration of E is equal to omega crossed with R of E relative to A. All right. Now what you can do over here is you can specify in this cell that this is VE like that, and then you'll get a variable which you can use, right? So you can just straight away go out and find out what the acceleration is by saying cross product of omega and VE, right? Because it's omega crossed with VE. And that will give you the right answer. But you can do the cross product straight away. You just have to be careful. What you can do is you can say cross of omega cross of R of E relative to A. Does that make sense? And you hit that, you'll get the same answer. All right. So you end up getting the acceleration. What I'm saying, the reason that I did it both ways over here is that going forward, you might see me use either one of these. So don't get confused, all right? Because it depends on how I'm feeling that day. Don't hate me for my feelings.
Could I ask
Right.
a question about something at the beginning of this problem?
Of course.
The absolute value of R AB.
Yes.
How'd you get 260? I'm drawing a blank on how to.
So the magnitude of 100 squared plus 240 squared should be 260.
Gotcha.
That's this the how you find the magnitude.
Yep. Thank you.
Guys, again, I'm going to tell you this. I expect you guys to understand vectors that, like, you know, they're your best friend. Like you take them out for a walk every morning and you cuddle with them at night. All right. That's the expectation going forward. You need to be able to know what cross product is, dot product is, how you find the unit vectors of things, and how you find the magnitudes of vectors. All right. Not super important for the exam on Thursday, but extremely important for rigid body motion. And if you need help with that stuff, let me know. You want me to just post the Khan Academy videos about vectors on Brightspace? You guys want to do that?
Yes.
Okay, all right. You got it. All right. Okay. So answer. Yeah. All right. So again, writing it in meters per second squared instead of millimeters per second square, we get minus 81.1 I hat plus 74.9 J hat plus 31.2 K hat meters per second squared. All right. Any other questions, guys? No? All right. Okay, so we go on to the next question. So you have two friction wheels A and B that are both rotating freely at 300 RPM counterclockwise. So counterclockwise like that. When they're brought into contact. After 12 seconds of slipping relative to each other at their point of contact, wheel B reaches a final angular velocity of 75. So reduces from 300 to 75 in the same direction. But if you notice, when there is no slippage between A and B, what's going to happen to A? Is it going to rotate counterclockwise or clockwise? When there's no slip, think of gears.
It's going to rotate clockwise.
Going to rotate clockwise. Why is it going to rotate clockwise? Because at the point of contact, when there is no slip, they have to be moving in the same, with the same absolute velocity in the same direction, right? That's just how no contact, no slip works, and that's how gears work as well. So this is kind of a prelude to when you guys go into looking at dynamics of machines and mechanisms. All right. So basically, all you have to keep in mind in this question is the one thing that you might not have known is that when there is no slip between two things that are rotating, at the point of contact moves with the same velocity. And when I say velocity, I mean magnitude and direction. All right. So what that means is that in the beginning, when they just come into contact, that's the color blue, right? So let's say you have that. And you have that, like terrible drawing, but you guys get the picture. You know what? Let me draw it separate.
Is this another problem from the problem set, like the one previous?
Yes, it's another problem from the problem set.
Did you put the number on it?
Yep, sure. This is problem 5. Thanks. So you got that. And then you got that, right? And they are in contact for all intents and purposes, right? I'm just drawing them separate so that it's clear what's happening. So in the beginning, it's black color. You have both of them moving counterclockwise, right? So this is moving omega A, this is moving omega B, and this has a radius RA, and this has a radius RB, right? Then at 12 seconds, when slipping stops, that's color red, right? So at t equals 12 seconds, slipping stops, right? What that means is that this point in contact is going to be moving with the same velocity. And because we know that B is counterclockwise after 12 seconds, we know that A is going to be clockwise. All right, so it's going to move with the same velocity V, right? So the point to notice is that A changes from being counterclockwise initially to being clockwise after 12 seconds. All right, and for all intents and purposes. So this is now we're going to use the slab theory, which I don't like to do, but people like to do, so I just have to teach it. Right, so you're just looking at one plane, and what we're going to do is we're going to consider counterclockwise to be positive. All right. Okay, so that's the positive z direction you can think of. All right, so then you have initially for your wheel B, you're told that that is equal to 300 RPM, right? So we can't work with RPM when we're looking at rotation. So you always must convert it into radians per second. Even if you're given degrees per second, you have to convert that into radians per second. And to do that, what you have to do is, you know that 2 pi radians equal to 360 degrees, right? Right? So that's radians per second. So this ends up being, can someone tell me what this is? No, that is not what I have.
5.2.
Wait, it's not 2 pi over 360. What did I do? I'm such an idiot. It's 2 pi.
180.
Pi r.
No, no. I'm an idiot and everyone else is wrong. It's 2 pi radians in 60 seconds, right? what a stupid mistake to make from my side. Yeah, it's not 2 pi over 360, it's 2 pi over 60. It moves 2 pi radians in 60 seconds, right? So what's this number?
31.4.
That's right. 31.416. And we know that this is counterclockwise. All right. Okay. Then for your B, at a time equals t equals 12 seconds, you're told that it is 75 RPM counterclockwise, right? So let's convert that as well. So you have 75 RPM. So that's 75 times 2 pi radians divided by 60 seconds, right? Right. That's when one revolution, that's what's happening, right? So RPM is revolutions per, okay, all right. Do you guys know what RPM is?
Yeah, revolutions per minute, right?
Revolutions per minute. It's okay if you don't know, that's totally fine. So one revolution is equal to 2 pi radians. 1 minute is equal to 60 seconds. That's basically what I'm doing to convert this into radians per seconds. All right, okay, so what's this number come out to be?
7.8.
I got 7.854, right? So radians per second. Let's go. This is also counterclockwise. So now from here, you can find out the acceleration of B, the angular acceleration of B. You know that omegas are in the same sense, right? So they don't change sign. So it's just going to be omega B at t equals 12 second minus omega B initially divided by your time period t, which is 12 seconds, right? So that's just going to equal 7.854 minus 31.416 divided by 12 seconds, right? So you get being minus 1.9635 radians per second squared counterclockwise, which basically means that in the counterclockwise direction, the velocity is going to be decreasing, or you could write this as being positive but in the clockwise direction, right? It means the same thing. Is that clear, guys? Okay,
Yeah.
next. Oh, sorry. Someone had a question?
No, I was just saying it made sense.
Okay, thank you. Yeah, so now, after 12 seconds, your slipping stops, right? And the point of contact has same velocity on both wheels. What that means is, because we know the motion of wheel B and it's completely described, we can say that the vector quantity, not the vector quantity, the scalar quantity of the velocity V is just equal to whatever the radius of that wheel is. And remember, we're looking at a slab, so we're doing this directly. You could do it with your cross product as well, which is how I prefer to do it, but this is the shortcut method that some people love and appreciate. Right, so that's going to equal, so the radius of B is 3 inches. Right, so that's 3 inches times 7.854 radians per second. And this, what does this end up being equal to?
$23.56.
That's right, 23.56. Let's keep it with 3 decimal places to be consistent throughout. Inches per second, right? And the direction of this, we know from the description of the problem, it's going to be downwards, right? So downwards, like that. All right, so now let's look at A. Oh, by the way, just let me know when I'm good to move on to the next page. Or let me know if I'm not good to move on to the, which is a better way to do it.
Just to clarify that, excuse me, the velocity that we just found, the 23 inches per second, is that the like scalar, right? Or
That's a
is it-
scalar, yeah. And now
Okay.
with this arrow, I know it's going to be downwards, right? So that's the vector direction. And the only reason you know this for this problem, come on, is the fact that the centers are on a horizontal line. So the velocity at the point of contact is going to be downwards, right? So this is, all right, now you guys are learning about machines and mechanisms. If this was like that, right, you just join the center line and it's perpendicular to that is where the point of contact is going to be. But again, you don't need to worry about this. This is just extra information. We know that it's going to be moving downwards. All right, guys, I'm moving on because no one's saying anything. Okay, then let's look at wheel A, what's happening. So for A, initially, it's moving counterclockwise 300 RPM. Right, so that's going to equal the same thing, which is, I'm not doing the conversion for you guys, it's just 31.416 radians per second, right? Do you guys understand the fact that despite them being different sizes, the angular velocity can be the same, right?
Yeah,
It's just they're sweeping the same angle in the same period of time initially. All right, so that's 31.416 radians per second. So now, no slip after 12 seconds, right? We know that the scalar quantity of the velocity is going to equal RA times whatever the scalar quantity for the angular velocity is, right? So this is equal to V over RA, and we found out V, the scalar quantity, that was just 23.562 inches per second, right? So plug and chug. 23.562 inches per second divided by RA, which is 2.5 inches, right? So 2.5 inches, units cancel out. So you're left with radians per second, right? So you get 9.4248 radians per second. And is this clockwise or counterclockwise?
Clockwise.
Clockwise, right? So it's going to be clockwise. But because we're looking at angular speeds and the changes in the counterclockwise positive direction, it's going to be negative for the sense that we need it to be in order to find the acceleration, right? When you're finding the angular acceleration, you need your angular velocity to be in the same sense. Otherwise, your signs are going to get messed up. Is that clear to everyone?
So you have to like write it in the fact that both values are going clockwise or counterclockwise. You just both have to be
Absolutely.
the same orientation.
Exactly.
Okay.
Yeah. So then you can write the angular acceleration of A is just equal to the angular speed. I should just start using speed for the scalar quantity, but angular speed at 12 seconds minus your angular speed initially, right? So that's going to be, and remember, we said we're going with the counterclockwise sense, so let's just go with that, right? So you have minus 9.4248 minus omega A, which was 31.46. That was positive. All right, so you end up getting minus 3.4034 radians per second squared. This is negative because it comes out from here, right? So this means that this is in that direction, or you could have it positive in the clockwise direction. All right, so this is your second answer that you were looking for. This was the first one.
Okay. I forgot you had to divide by 12, and I was like, where did you get that? But
Oh
I
yeah,
got it.
sorry, my bad. No, absolutely, dude. Everyone has to call me out for this stuff like this. I am terrible. As I'm growing older, I'm becoming the epitome of that absent-minded professor kind of person. It's terrible. All right, the last part of the problem asking you to find the time at which the angular velocity of wheel A is equal to 0. So what does that mean? That means that between the period of this being starting off rotating counterclockwise and it ending up being clockwise, sometime in the middle, the angular velocity would have had to be 0, right? Does that make sense to you guys? And that's it. That's all you're solving for. So basically, you're going to do is you're going to find t when omega is equal to 0, right? And we know from the expressions that we've written out for a constant acceleration, which is what we're assuming in this problem, by the way, constant acceleration is equal to the initial speed plus your angular acceleration times time t, and we know that that is equal to 0. So you can say that t is equal to minus omega a at 0 divided by the angular acceleration of a, right? We know that this is minus 31.416. And again, you have to keep the sense the same in both of them. So same direction. We're just going with using counterclockwise positive throughout this problem, divided by minus 3.4034. Right? This is in radians per second. This is in radians per second squared. You're left with seconds. So you get time equal to 9.23 seconds. And please check that. Again, the answer could be very wrong over here.
That's right.
Yeah, works for me.
All right, thanks. Mental check, 9.23. We know that it goes from counter clockwise to clockwise in 12 seconds. So we know that it has to be 0 in between 0 and 12. And yes, thank you, mathematics. 9.23 is in between 0 and 12. So mental satisfaction as well. All right, good. Okay.